Theories are similar, but they give us a very, very broad yet detailed description of something. So I know that sounds a little counterintuitive, but it will take a big topic and give us very, very specific thoughts about that topic. Okay? Examples of this could be atomic theory, wave theory, all those types of things that are broken down, and they've given us specific details about those. Okay? There's lots of different atomic theories, but they've grouped into one. Okay? Lots of different atomic models, but we look at atomic theory as a whole. Okay? Okay, and last but not least is our laws. Laws are very certain, concise statements about how something behaves. Okay? Newton has how many laws? Anyone know? Yeah, 3. Okay, Newton has 3 laws. This, for example, is the second law. Force equals mass times acceleration. Okay? We talk about the law of conservation of energy, law of conservation of matter. These laws have come about because they've been found experimentally valid over tons of trials. Thousands and thousands and thousands of trials. You can't just think of a hypothesis or think of something you think might be true and call it a law. Okay, a law is tested and tested and tested. Okay, so laws are the most certain scientific truths that we have, okay? They are found almost experimentally, or I guess absolutely experimentally true up to this point, okay? So all the equations that we do, everything like that has been found experimentally valid over thousands and thousands and thousands of trials because it works every time, okay? So all of these equations that we'll learn have been proven true over and over and over and over again. Okay? All right. Let's talk about measurements, accuracy, precision, things like that. We want both accurate and precise measurements in all of our physics experiments, all of our trials, things like that. When we talk about the difference between accuracy and precision, can anyone tell me what that means right off the bat? Yeah, Gabe, what do you think? Just a second. Okay. When we take measurements, we want both accuracy and precision, but there's a certain amount of uncertainty that we have in each measurement. Okay? And those things can be limited to either the instrument we're measuring with or error in our human ways in general. Okay? There can be lots of different things that cause us to have error, but there's always a certain amount of guessing or estimating when we take measurements. When we take a measurement, the best way that we do this and to kind of get rid of as much uncertainty as possible is we read what the instrument gives us. So in this case, this is a meter stick. The big numbers here are centimeters, and there's little tiny marks in between for millimeters. Okay, does that make sense? So there's millimeters that are marked on this meter stick. Okay, so we would be able to read precisely or accurately to the millimeter mark. Okay, so what we do after that is we estimate one more digit. We read what the instrument gives us and we estimate one more digit. Okay, does that make sense? So here we should be able to read to the millimeter, and then we'll take a guess in between those next 2 millimeter marks. That can make sense? So every reading we take from a meter stick should have 2 decimal places. Okay, if I'm saying it's 42.2 centimeters, it can be 42.20 centimeters. Okay, because that 0 would be my estimated digit. Does that make sense? gives us a little bit less uncertainty in our measurements. Okay? All right, so here's accuracy and precision. Accuracy is how close we are to the actual measurement, okay, the actual or the accepted measurement. So accuracy is close to actual, okay, the accepted value. When we do trials, we try to do more than one measurement because we don't want our one good, accurate measurement to be a fluke. Okay, we want our average of our trials to be a good, accurate measurement. That's close. Okay, if we take 10 readings and only one is even close to the right value, that means our measurements were not very accurate. Okay, not only were they not precise, the average wasn't accurate. Okay, so we've got to take multiple readings so that we can get the average close to that accurate or accepted value. Okay, does that make sense? Multiple trials. Okay, precision is how closely our measurements are related to each other. So we might not have very accurate measurements, but they might be really, really precise. Okay? That means one side of it is good, one side of it is bad. We want both of those things. Okay, so if I'm reading an instrument incorrectly, okay, if I'm really supposed to be measuring 42 centimeters and I'm reading it as 52, I'm measuring this inaccurately, but I'm doing it over and over and over and over again, right? So my measurements would be precise, but they would not be accurate. Do you see what I'm saying there? Okay, so it's all about reading the instrument both accurately and precisely. Because if I misread this instrument over and over and over again, I'll have precise measurements, but not accurate measurements, and we don't want that. Okay? When we're doing an experiment, the best way to kind of keep both accuracy and precision in check, hopefully both of those in check, is to have the same person measure every single time. Okay? To have the same person measure a particular set of trials. Okay? And the reason is because I might read the meter stick or the instrument much different than McKenna reads it. Okay, we might just be a little off on our eyesight. We might be a little off on the height at which we view an instrument. We might be off at the angle at which we view the instrument. All those kinds of things can skew our measurements a little bit. Okay, so throughout a trial, it's best to have one person do all of the readings so that you can have a precise measurement and hopefully accurate as well. Okay? Okay, here's our percent error equation. This should be nothing new, right? You calculated percent error hopefully in chemistry or college chemistry at some point. Okay, definitely college, if not, I don't remember if we did it in honors. Okay, so accepted is the real value, measured is what you got, divided by the real times 100. Okay, and we're going to use that measurement or that equation today in an activity we're doing, so you need to make sure that you have that equation in your notes. What do the little bars mean on the outside of the numerator? Absolute value. Good. So you should never have a negative percent error. All right. Let's talk about significant figures, everyone's favorite topic. So let's look at our rules for significant figures. These should hopefully be a review. These are ones we go over in chemistry and college chemistry, I'm sure. So all non-zero digits are significant. That one's the easiest rule to remember. Anything that's not a zero always counts. Zeros to the right of digits after the decimal point are significant. How many sig figs this number has? 3. Good. And what about this number? 3, also 3. Okay, to the right of digits after the decimal point, both have 3. Why are these two zeros in the 5.00 considered significant? Yeah.
Does that tell you how precise your measurement is?
Exactly. They're telling us how exact our measurement is. Okay, if we just wanted to be about 5, we would have just put 5. Okay, but if we want to express that it's 5 exactly, we say 5.00. So those two zeros become significant as a way of us expressing how exact our measurement is. Okay, very good. All right, zeros to the left of digits are non-significant. They just are considered placeholders. Okay, zeros to the left of digits. And that's either before or after the decimal point. Okay, any zeros to the left of digits before they start are non-significant. All right, Raven, what do you think? How many sig figs here?
3.
Do we agree? Raise your hand if you agree. Yeah, very good. Okay, zeros to the left of to the left of digits, whether they're before or after the decimal place, are non-significant. So both these guys we don't care about. Okay, non-significant. Very good. Any questions there? All right. Zeros between digits are significant. That rule sometimes goes unsaid, but it is important. Zeros between digits are always significant. Okay. And all digits in scientific notation are significant. Those are our main rules right there. When we talk about scientific notation, tell me how many significant figures are in this expression? 3. Why not 7 or 6 or whatever it is, the expanded form? Yeah, Alexis? If we move the decimal, I would move it this way. Sorry, I'd get bigger. The reason that they're non-significant is it's just the face value. Okay, we only want what we can see, and if we expand it, not only will it become ambiguous, which we're going to talk about here in a second, but we don't know how exact that measurement should be. Okay, when you put things into scientific notation, you lose some of that exactness, okay, because you're abbreviating it. So we don't know how exact the measurement should be. Okay, so it's just the face value, just exactly what you see here. Okay? We're going to talk about ambiguous numbers. Does that word sound familiar or no? Yeah? Okay. So ambiguous numbers are ones we don't know how many significant figures there are. Okay, for example, 120,000. Ambiguous numbers have what I call trailing zeros. So these zeros right here, I call them trailing zeros. Okay, I don't know if that's made up or not, but that's what I call them. Okay, they have a 0 with no decimal point, no scientific notation, no nothing. Okay, so we don't know if they're trying to tell us it's about 120,000 or it's 120,000.0000. You know, we don't know what they're trying to say. Okay, so this particular number could have 2 sig figs, it could have 6, it could have 8 if you put on 2 decimal places, it could have as many as you want. Okay, so the way that we correct an ambiguous number is to use scientific notation and put that number into scientific notation, or we correct it by adding a decimal place. So those are 2 ways that we can correct an ambiguous number. It just really depends on the number of significant figures that our measurements call for, okay, or that our rules call for. So if I put it into scientific notation, I can get down to 2 significant figures. I could add 1.20 times 10 to the 5th and be at 3 sig figs. I can alter that however I want. Okay, scientific notation is very easy to give the exact number of significant figures you want. If I can have up to 8 sig figs, I can add 2 decimal places, and that gives me a very, very, very exact number. Okay? So we can range these all the way from extremely exact to a pretty rough number. rules, we can go through these pretty quickly. When we talk about math rules for significant figures, we're looking at doing the math just like normal, and then we round our answer to the fewest number of significant figures given. Okay? So math like normal, then we round to fewest number of significant figures. This is for multiplication and division. Okay? Do the math just like normal, like I've done here. Okay, and does this answer have the correct number of sig figs? Some people are shaking their heads. I say no. How many should we have? Just 2. Okay, so all we do there is round it. Okay, you could just round that number to the next whole number if you only need 2 sig figs. You could make it 7.7 times 10 to the first if you want. There's not really any point in that. Okay, that would still give you 2 sig figs. Okay, but because this value right here only had 2 significant figures, that means our answer can only have 2 sig figs. Yeah? Okay, addition and subtraction rules now. When we add or subtract, we do the math just like normal, but the result or the sum or the difference of those can have no more decimal places or be no more accurate than one of our original measurements. Okay, than our least precise measurement. So when we add and subtract, we look at the number of decimal places that we started with, not the number of significant figures. We add and subtract, we look at the fewest number of decimal places and round our answer to that. All right, so is my answer correct? No, what should it be? Yeah, just 3.0. Okay, I want 1 decimal point because up here of my 2 measurements, I was given a 1 decimal point and 2 decimal points, so I want to round to the least number of decimal places. Okay, and that gives me 3.0. Very good. Okay. Moving on now to SI units. What's the nickname for SI units? Yeah, the metric system. Good. Okay, the metric system. Okay. The metric system is used universally, okay, throughout the world as a consistent form of measurement. Okay. Does the U.S. use the metric system exclusively? No. We have to have our own system, right? So now we have to learn to convert to the metric system because the metric system is scientifically the most universal. Okay? So here are some base quantities in the metric system that you need to know. Okay, so this chart needs to go into your notes, and I would like you to have the first 4. Okay, length, mass, time, and temperature. You don't need to have the last 3. Okay, we won't get that far. You do need to know those first ones. So they are very, very easy to convert with. I'm going to put up a chart of all of the SI prefixes. And I'm going to explain the chart just a little bit before you get started writing it down. Okay, so just give me a second. Okay, here is all of our SI prefixes and the order at which they go in. Okay, so I want to explain it just a tiny bit. First of all, you only need to go from nano to mega. Okay, those are the ones that are most often used. Those are what you'll have to be in your notes. But just give me 1 second. Okay, tell me where on this chart the base fits. Right, just the regular gram or the regular meter. Between what 2 of those prefixes does it fit? Deci and kilo. Very good. Okay, so the base would fit somewhere right in here. Okay, that would be just the gram or the meter, liter, whatever it is. Okay, it fits right there. So our things above this line smaller or larger than the base? Yes, these values right here are all smaller than the base, okay? Much smaller. So the way this chart reads, it's telling us that a decimeter would be 0.1 of the base, okay? Or 1/10 of the base, 10 to the negative 1 meters, okay? Just like the centa would be 1/100th of the base, okay? So 1 meter would equal 100 centimeters. Does that make sense? Yeah? You can turn it around. Okay, it would be my preference for me to write them down to say 1 meter equals 10 decimeters. 1 meter equals 100 centimeters. 1 meter equals 1,000 millimeters. That would be my way of writing it down. That's easier for me. Whatever works better for you is fine. Okay, so you can interpret this chart and write this chart down, whatever works best for you. Okay? So the things below the line, the kilo and the mega, those are both bigger. So right here it's saying 1 kilo is 1,000 of the base, 1 mega is 1,000 of the base, or I'm sorry, 1,000,000 of the base. Okay, so go ahead and start copying this chart down. You can copy it either way. If you have questions about how to spin it, kind of, let me know. A US conversion, and we're going to do an SI conversion. Are all of you familiar with the Teechart system for unit conversions? Yeah? Okay, perfect. That's what we're going to use. Okay, so first thing you do in a Teechart unit conversion is you write what you know. Always write what you know. 193 inches, that's what we start with. And we're doing a US system conversion here. So if we want to go from inches to miles, what's our logical sequence for that? Inches to feet and feet to miles. Very good. Okay, that's it. 3 steps. So we write what we know, and we make our T. Okay, if I want to start working through my T-chart and I want to get rid of inches, where does it go? On the bottom, very good. And I want to go 2 feet, so it goes on the top. I usually give the bigger unit the 1, so between feet and inches, which is the bigger unit? Feet, so there's 12 inches in 1 foot. Now I'm done with inches. And if I want to go from feet to miles, I put feet on the bottom so I can get rid of that. Which of those between the two is the bigger unit? Miles. So tell me how many feet are in a mile? 5,280. Very good. 5,280 feet. So I'm done with feet. Now I'm left with miles as my unit, which is exactly what I want. Okay, so to solve this T-chart, you multiply across the whole top, divide by the whole bottom. All right? So you should take 193 divided by 12 divided by 5,280. Okay, or you could take 193 divided by parentheses 12 times 5,280. Should you get a big number or a small number? Small. Good. You should be expecting a small number, so just pay attention to that. What did we get? 0. What did you tell me? 3.04 times 10 to the negative third. Okay. Or 0.003. Okay. Very good. Do we all agree? Okay. I'm not concerned with significant figures in unit conversions. Okay. Those are hard to keep consistent. So I'm not worried about significant figures in unit conversions. All right, let's do our SI unit conversion now. Start with our millimeters, and we'll go to meters. So write what you know. What's our logical sequence here? Yeah, just go right to meters. It's only 1 step. You can go directly from millimeters to meters. So I want millimeters on the bottom, meters on top. Which of those is the bigger unit? Meters, very good. And how many millimeters are in a meter? 1,000, very good. Very good. So all I need to do here is slide the decimal place 3 positions to the left. So which one was easier? The bottom one, right? SI units are generally easier to convert, okay? And I know that seems a little counterintuitive since we know the US system so well, we know the unit conversions, but the SI unit is much simpler, much quicker to convert to and from, okay? Generally, it's less steps. All right, let's look at conversion factors between US and SI. These you need to have down in your notes as well. These three are the most important. Okay, inch to centimeter, foot to meter, and pound to kilogram. Those are our most important, or most often used. So just kind of quickly before we really get going here, I want to make sure that you understand the importance of consistency of your units throughout a problem, okay? I know it's easy to drop units when you're doing problems, but it's really important that you understand the consistency that you need, okay? You cannot deal in physics problems half in grams, half in kilograms, or half in centimeters, half in kilometers. Okay? You've got to make sure that when you start a problem, you've got everything into consistent units. Otherwise, your entire answer could be off by powers of 10. Okay? Especially when we're working in the SI system, which we will. Okay? We've got to make sure that those are really, really consistent. Okay? So just make sure that you're checking that as you go through problems. I know it's easy to skip over. I know it's easy to drop units, but I just ask that you pay special attention to that. Okay, in all of your T-charts, you've got to keep those units in, otherwise inevitably you'll flip one by accident. Okay, so just keep units in so you know everything's canceling, and then when we get into real bigger problems, just make sure that those units are consistent to get your problem started. Okay? All right, let's try a little bit more complicated T-chart conversion here. 90 kilometers per hour to meters per second. So I'll give you a second to get it written down, and then we'll get started with the difference in this T-chart. All right, the only thing that changes here is that since we have a unit of kilometers per hour, okay, the per means divide by. So we've got to take kilometers per hour. This kilometers per hour is a velocity or a rate, okay, and rate is distance over time. So we're saying essentially that we traveled 90 kilometers in 1 hour. That's what we're starting with here. You don't have to put the 1 in, okay, that doesn't make a difference, but you do have to separate those units. Okay, you cannot have kilometers per hour on top and nothing on the bottom because your numbers won't work out. Okay, so we want to start with kilometers on top, hours on bottom. Let's start our conversion now to get it to meters per second. You can get rid of either kilometers or hours first. You choose. Kilometers. Okay, so we want to go from kilometers to what unit? Meters. Good. And which is the larger unit? So kilometers should get the 1. And how many meters are in a kilometer? 1,000. Everyone seems to remember that kilo means 1,000, but a lot of people get turned around thinking that there's 1,000 kilometers in a meter, and that's not how it works. Okay, kilo means 1,000 of anything, 1,000 of the base. Okay, so try not to get that one mixed up. That's really, really a common switch. Okay, so kilo means 1,000 of something. Kilometer almost always gets the 1. Okay, or kilogram or whatever. All right, so we're done with kilometers. We're left with meters, which is what we want on top, because we want meters per second. Okay? So let's get rid of hours now and go to seconds. Hours goes on top. Do we need to go hours to minutes to seconds? No. How many seconds are in an hour? Very good. Okay, you could do the extra step if you want, hours to minutes to seconds. It's just one more step in your T-chart. So we're left with meters per second, which is exactly what we want. So we multiply across the whole top, divide by the whole bottom, and we should get 25. Perfect. Very good. How many centimeters are in 3.2 miles? This one you're going from SI to US. So you've got to use one of those conversions that I gave you in that last chart. There's two different ways you can do this. You'll get a little bit different answers. That's okay. Always start with what you know. So a couple different ways you can go about this. How many of you chose the top way? Yeah? Miles to feet to inches to centimeters, yeah? And then how many went about the bottom? Miles to feet to meters to centimeters. We'll have two different answers, okay? And they seem quite a bit different, but it's because that feet to meters conversion could be a little bit more exact, okay? That's the difference there. So it doesn't make a difference to me, as long as the work looks right and your answers are in the ballpark. That's what we need, okay? So what did you get here? Like about 50,000 something? Or did I make that up? Yeah? 50,000 something. Okay, Michaela, why don't you tell me what you got?
I got 514,929.
That 0.08. Okay, which method did you use?
I used the top.
Okay, what about someone that used the bottom? Morgan, what'd you get?
506,880.
Okay. See, they seem pretty significantly off, but that's okay. Okay, last two on your own. How do we even start the first one if we're not given a number? Yeah. We know how many days are in a leap year, I hope. 366?